Hi, my name's Gary Schofield from Total, and it's an absolute pleasure to be joining you today. I'd just like to thank Tarmac for the opportunity to speak to you. What I want to speak about today is particularly focused on bitumen and the contributions that it can make, the important contributions that it can make towards the sustainability of asphalt. I think as time's going on, it's becoming increasingly important to recognise the criticality of sustainability, not just in terms of the environmental issues, but also in terms of costs, monetary costs, and in terms of public satisfaction as well. So what I want to do today is take a look at how bitumen, some of the thought patterns that go into it, and some of the thought patterns that must be going into the selection of bitumens for these sort of applications. Particularly thinking about the bitumen side, there's many selections out there. There's many materials that you can choose from, whether it be hard paving grade materials, whether it be normal paving grade materials, whether it be polymer modified bitumens. And that's the start point at which the specifier has to really start to understand not just the criteria which the road is going to be subjected to, but also the performance that the bitumen is going to be able to contribute to the asphalt. So, if you like, we're putting these things through a little bit of a filter, a funnel, so that we put everything in to start with, and we shake it through so the answer comes out at the bottom. But in order to do that, we have to really understand. It's no good just putting on the specification we want a PMB, polymer modified bitumen, because what does that mean? It could mean anything. So we not only need to filter through for the right decision, so it's not just which paving grade you want, it's not just which polymer modified bitumen you want, it's not just whether you want it as hot mix or as warm mix, but we need to understand the detail of what's expected of that bitumen. Okay, now I want to focus very much on polymer modified bitumens because I see there's going to be an increasing use of polymer modified bitumen because of the real benefits that they can offer in terms of resistance to road stresses and the contribution it can make towards durability of the asphalt surface. We can look at the impact in terms of the polymer modified bitumens and how stiff they are. Okay, whether they're very hard bitumens, i.e., very stiff, or whether they're very soft bitumens, or i.e. they have low stiffness, but also in terms of the polymer impact, whether it's low polymer impact or high polymer impact. Now on this graph, I resisted putting low polymer concentration and high polymer concentration because it's never as straightforward as that, because it depends very much upon the bitumen source that you're using as to how influential that polymer content is going to be. It depends upon the type of polymer you use. It depends upon whether or not you cross-link those polymers. So rather than saying polymer content, I've talked about polymer impact because it is so dependent upon many different factors. So if we think about the behavior of the polymer modified bitumens in terms of these criteria, the styrofoam range that we manufacture at Total, we can put on this chart where the different grades are. So our Styrof X70, which is effectively our basic grade, if you like, of polymer modified bitumens, they're going to lie at the lower polymer impact. So these are a slight improvement on penetration grade materials. Being a 70 pen, it's sort of average sort of penetration. We can then move to something like a Styrof XL50, which is a mid-range polymer. So we've moved further along the polymer impact scale because we're getting much more benefits coming from that polymer impact. And what that means is that we're going to see better resistance to a lot of the stresses that the road's subjected to. But again, we need to understand the specific stresses we're talking about. We're going to look at that in a little bit. And finally, the top of the range material is something like the Styrof Extreme 100, which, as you can see, is right towards the high polymer impact end, but right at the top of the low stiffness, because it's a very soft bitumen. And of course, the reason that I believe we should be looking for these softer materials is that yes, it has to resist the stresses sufficiently, but bitumens are only going to get harder with age. So for me, if we can select the softest material possible, then it allows us to have that bitumen on site for longer before it reaches that critical stiffness at which it's going to start cracking. So you can see where we're lying there with the types of products that we manufacture within Total. What I want to look at now is some of the stresses that are going to be applied to the asphalt and how these bitumens will contribute towards resisting those stresses. So let's have a look first of all at dynamic deformation. So you're going to see improvements in performance if you go along the high polymer impact or if you go down towards the stiffer materials. So when we're talking about dynamic deformation, we're talking about the impact of the traffic moving over the road. Of course, the road itself is a flexible material, so it's going to give, but we always get left with a partial, very small amount of microscopic permanent deformation. So the stiffer the material is, the less it moves in the first place. So the less permanent deformation you have. So if you want dynamic deformation, you can go very stiff materials. But also you can go with higher polymer impact because that means the road becomes more elastic, so it recovers more. And with something like Styrolf Extreme 100 right at the far end of the polymer impact scale, where we've got a high polymer impact, we're getting really good recovery. So that means that the amount of permanent deformation, even though it's quite a soft material, the amount of permanent deformation is restricted. Okay, so what we would say is that you wouldn't choose something where you're going to have concerns about dynamic deformation. I wouldn't be using something like a Styrolf X70 because it's not got the contribution there from the polymer that it needs to resist that dynamic deformation. If you look at something like a mid-range polymer, in this case the Styrolf XL50, we're looking a little bit stiffer because it's a harder bitumen, but of course we've only got a mid-range polymer impact. So it could do some good. It depends upon the particular design you're looking at, but it's going to contribute from being stiffer and it's going to contribute from having an interim polymer impact. And then, of course, if you look at the Styrolf Extreme 100, it's not stiff at all. It's very low stiffness, but it has such a high impact from the polymer that it can resist because of the amount of recovery that it's going to give. Let's look at that in a bit more detail. We can talk about this MSCRT test, which is one of the European test methods, where you're effectively sticking a little bit of bitumen. You're sticking together two plates with that bitumen, and with the top plate you're applying a 1 second predetermined stress to it, and that results in the lower plate moving as the bitumen strains. The stress is removed for 9 seconds, so it allows that a little bit of recovery, and then it's repeated 9 times. Okay, a further 9 times, so a total of 10 actions is looking at that. And what we're measuring on this is the amount of recovery that we get back from that stress that's been applied, and it's averaged over those 10 periods. We also want to look at the effective amount of permanent deformation we're getting. And when we can translate that graphically, what I've done, I've sort of inverted the whole impact here. And so we're looking at the propensity towards dynamic deformation. So the further down these bar charts are going, the more likely it is to be subjected to deformation. And the different colour bar charts here are the different temperatures at which the test has been done. So if you look on the far left of the graph, we can see we've got an Asphalt 150. So that's a basic penetration grade bitumen at 125 pen. And you can see that the red colour, i.e. 30 degrees, you're getting a degree of resistance there to deformation. But as soon as you get the green bar coming there, i.e. 40 degrees C, it's giving up the ghost. So at 40 degrees C, it's going to start deforming. As you move towards a slightly stiffer material, i.e. an 85 pen, you can see you get a bit better resistance, but still not great. If you then move towards something like an XL70 mid-range polymer, what you can see that even at temperatures at 50 degrees C now, we're still getting a little bit of resistance, but it's starting to go. You can see between 40 and 50 degrees C, you're starting to see a difference. And at 60 degrees C, it's definitely going. But right at the extreme of the polymer impact, we have the Styrolf Extreme 100. And you can see that at 60 degrees C, even at 60 degrees C, the impact, even though it's a soft bitumen, the impact is fantastic because it's that elastic recovery which is stopping that permanent deformation from occurring. So you can see that whilst, even though it's sort of contrary to what you might expect because it's low stiffness, it's very polymeric and very elastic, and that helps resist that dynamic deformation. If now we started thinking about fatigue resistance, we see a very different picture because we see the fatigue resistance improving as we go softer in the bitumen, and again improving as we go up the polymer impact scale. So when you're thinking about fatigue resistance, you wouldn't necessarily choose an X70 bitumen. You might consider your Styrolf XL50 because you've got that polymeric impact coming into play. But you'd certainly consider the Styrolf Extreme 100 because it's not only low stiffness, but it has a huge amount of elastic recovery again. So if we consider that, this is a test, again using the same equipment as the previous slide, where you stuck together a top plate and a bottom plate. But with this one, what you're doing, you're applying a known strain to it. So you're moving it a certain distance. And again, the bottom plate follows it, and you're measuring the amount of force required to move it. Effectively, what you're measuring is the G star, the complex modulus, but we can consider that as strain effectively. So the vertical axis here is measuring the complex modulus, or the stiffness of the material initially. Because what happens is as you repeat that strain, because this test is a repeated strain test, so as you repeat that strain over several cycles, what happens is that you start to develop microcracks and the amount of complex modulus drops. And we're measuring here the amount of stiffness that's retained in terms of percent, so percent retained complex modulus after 30 minutes of repeated strain. Okay, so hopefully that'll make sense as we start to look at the graph. So with a 5% strain, so just a low level of strain being applied, what you can see is that the 4060 bitumen is quite stiff, as you'd expect. Styrolf XL70, because it's a softer bitumen, has a much lesser stiffness. The Styrolf Extreme 100 lesser again. But what we do see is that after 30 minutes, we have almost 100% retained stiffness with the Extreme 100. So that's showing it's very elastomeric and resistant to strain. It's still, after 30 minutes, capable of relaxing the strain that's been applied to it. The Styrolf XL70, possibly not quite as good, but still reasonably good. And the 50 pen, not particularly elastomeric at all, but it's still, after 30 minutes, retaining about 70% of that initial stiffness. So at 5%, very low levels of strain, we can see that picture. If we then move to 10% strain, see a very different picture appearing, because all of a sudden the 4060 can't cope with that level of strain. It starts to crack quite readily. And you can see that after 30 minutes, you're left with only about 15% of the initial complex modulus left. So it drops off rapidly. The XL70, just over 50%, so it's better, but nowhere near as good as the Styrolf Extreme 100. If we move then up to 15% strain, the differences are exaggerated even further. So what that illustrates is that the capacity of Styrolf Extreme 100, i.e. at the high end of the elastic, of the polymer impact, sorry, the Styrolf Extreme 100 can cope with the repeated strains. So in other words, it's good in fatigue resistance, much more so even than the Styrolf XL70, and definitely more so than the 4060 pen. We can also consider fretting resistance, because of course fretting resistance is very important in terms of durability. You don't want to be losing those surface aggregates from the surface of the asphalt. So again, if we look at where the impacts are going to be improved, it's again towards that high polymer impact, and again towards the sort of lower stiffnesses. Because if the material's too stiff, and a fast force is applied to it, that bitumen is likely to fracture, and you'll lose your surface aggregates. So again, the Styrolf XL70 is not going to be great at resisting fretting resistance. Your Styrolf XL50 will contribute to it because it has a better polymer impact than the Styrolf X70. So it's a small tick in there. But of course, your Styrolf Extreme 100, because of the high polymer impact, will have a big tick in there. And that's because one of the key factors in resisting fretting is the ability of the asphalt to relax after strain. Okay, so as I mentioned before, it's very often on where you get fast stresses that are impacting on the surface aggregates that you lose them. That's what fretting's all about. But if the binder doesn't have that capability to move with that in that fashion, to move, if the binder can't move with the aggregate and recover, then the aggregate will be lost. So elastic recovery is critically important in this area. So if you look at a 4060 pen, for example, normal penetration grade bitumen, you can see that at 10 degrees C, elastic recovery, 25 degrees C elastic recovery, and 60 degrees C elastic recovery, not great. You know, it's not really contributing anything towards elastic recovery. So it's all about the capacity of the bitumen to hold itself. Yeah, and once it goes past that point, it's going to flip out. If you now consider the X70, you can see that you're getting significantly higher elastic recovery at 10 degrees, much more at 25 degrees, and a little bit more at 60 degrees C. So it's quite temperature susceptible. Move towards an XL70, you've now got 65% recovery down at 10 degrees, 80% at 25 and 60% at 60 degrees C. So we're starting to improve that elastic recovery all through the temperature range. And of course, Styrolf Extreme 100, phenomenal amount of recovery, even down to 10 degrees and up to 60 degrees C. So that's why that type of binder is so good at resisting fretting from surface stresses. We now consider resistance to ambient temperature variations. I think this is an area we have to consider more with climate change. They keep talking about the potential for extreme weather conditions. So resistance to ambient temperature variations is becoming increasingly important. And again, one of the key factors in that is the amount of polymeric impact that we can see. So again, X70, not really going to have much impact. Styrolf XL50 have a little bit of impact, being an intermediate grade polymer, but the best of all will be Styrolf Extreme 100. And if we can look at that, because bitumen is a strange material. You know, bitumen behaves in a way which is very different to the way our brains operate, because we tend to think of things as pure solids and pure liquids. So, you know, water, for example, we think about water, you get home of an evening to get your gin and tonic, you get your ice out of the fridge and it's absolutely solid. But as soon as it reaches 0 degrees C, it turns to a pure liquid. Bitumen's not like that. Bitumen shows both solid and liquid characteristics at the same time. And it depends where you are on the temperature scale to resist flow. So if you look at this graph here with a penetration grade bitumen, you have a range of performance, a range of temperature, where you're getting good performance. But then you have a critical temperature above which the bitumen is really just becoming too soft. It's still got some solid contribution, but it's a little bit too soft to fully resist the engineering forces that are being applied to it. Similarly, to lower temperature, the solid impact is starting to take over and it's starting to become too brittle. So you have a range of temperature here at which you have good performance, good engineering contribution. Above that, it becomes too soft, and below this critical temperature, it becomes too brittle. Well, of course, if we're talking about climate extremes, we could well be, you know, in hot summer periods, be delving into this area where it's too soft for penetration grade bitumen to cope. Conversely, in winter, where we're having extreme cold weather, we could be in this area where the bitumen becomes too brittle to be of much engineering use. So what we're trying to do with polymeric intervention is we're trying to stretch those areas so we get an enhanced performance in the middle, so a better performance than just penetration grade bitumen, but we're widening that temperature range significantly. The other behavior pattern of bitumen is that it's what's called viscoelastic, so it's susceptible to strains, it's susceptible, sorry, to, I do apologise for that, phone ringing, it's not the wife this time, but what we're looking for is the frequency of force, because at very fast frequency forces, the bitumen can't cope and it becomes too brittle. And at very low, almost static forces, it becomes too soft and it becomes deformable. So the frequency of force has to be understood as well. And the contribution of the bitumen, the contribution of the polymer means that we can stretch the frequency of force at which it becomes too brittle. The reality is that it doesn't do an awful lot to the bottom frequency force. In other words, with static forces, static creep, the polymer doesn't have time to recover, because polymer impact, elastomeric polymer impact, is all about giving and then recovering, giving and then recovering. But if that force is constant in a creep type of situation, the polymeric impact doesn't have time to recover. So it does keep going. So with the frequency of force, it's very, very important at the high end, the high frequency forces. What that translates to in terms of temperature is performance. You can see with Styrolf Extreme over a much wider temperature range, somewhere between sort of 80 down to -20 degrees, -25 degrees C, compared with a 4060 that's probably sort of -12 up to about 50 degrees C. So this is the impact. The mid-range one you can see around about +60-ish down to about -20. So again, mid-range polymers are starting to give significant improvement, but the extreme, the high polymeric impact gives a really good protection against ranges of temperature. So if we just return to that thought about static creep resistance and look at the type of bitumen that you want to be using in your asphalt in that sort of situation, that is all about bitumen stiffness. As I said before, the polymer won't help it. If it's an elastomeric polymer, it's not going to help it much because it's not getting time to recover. And that's how the elastomeric polymers act. So something like X70 is a little bit too soft. Something like XL50, because it's a harder, stiffer bitumen, that's going to work reasonable. Styrolf Extreme 100 this time won't work because it's soft. It's low stiffness. And static creep resistance is all about stiffness. So the stiffer you go with your bitumen, the better the performance. So we've looked at a few different areas there of performance, and I think we can summarize that, if you like, on a radar graph. And you can see this is the bitumen contribution towards asphalt performance in all different manners. So it's the holistic performance, if you like, of the asphalt. If we then compare the 4060 pen against an X70 bitumen, you can see that you're starting to get slight improvement in terms of resistance to fretting and raveling, for example, around this area. You're getting an improvement in performance there. You're getting a slight improvement in areas of reflective cracking. But static creep, because 50 pen is stiffer than an X70, it's a worse performance. If now we start to look at an intermediate grade polymer, something like an XL70, then you start to see more significant improvements in terms of reflective cracking, because you've got that elastomeric impact starting to help. We're seeing the same for the same reasons in terms of thermal cycling. We're seeing the improvements in terms of dynamic deformation, because again, you've got this elastomeric impact starting to contribute significantly. benefits are also asphalt durability is impacted in many areas. One of the key areas is in material selection. So it's critically important not to be blasé about that, but to think about it seriously and to really understand it. We know that cross-linked polymer systems can have a significant beneficial impact on it. And we talked about war and mix, and we've got to ask the question, why wouldn't you use war and mix? It must be the future norm. And we must start thinking about value engineering. We must focus on durability and life costs and not just initial costs. So the message from me in this, really please consider sustainability through durability, because I think that is the way forward. Thank you very much.